You've built Spring Boot apps, written REST APIs, and shipped a service or two. Level 4 is about what happens after that, running Java in production, at scale, under real failure conditions. In this video we'll wire up Spring Data JPA and Spring Security the way a real team does, break a monolith into microservices with the resilience patterns that keep one bad dependency from taking down everything, use Java's newest concurrency tools including virtual threads, and finish with the testing strategy from fast mocks to real databases and containers that let you ship all of this with confidence. First stop, Spring in production. Not just wiring a controller to a repository, but the query patterns, pagination, and security you need once real users and real data show up. Spring Data JPA can generate a query just from a method's name, no SQL, no annotations. Find by email and active true parses into email equals this, and active equals true. Find by last name starter within your case becomes a case insensitive like. Spring parses these into JPQL at startup, so a typo in the method name fails immediately instead of blowing up at runtime in production. Derived names only get you so far. Once you need joins, aggregation, or the query is just clearer written out, drop into JPQL directly with that query, binding parameters with that param instead of concatenating strings. That's not just cleaner, parameter binding is what keeps these queries safe from SQL injection in the first place. Returning every row works in a demo and falls over the moment a table has a million orders. Accept a pageable and return a page of results. Instead it carries the content plus total elements, total pages, and whether there's a next page, which is everything a paginated API response needs. Spring Security wires a filter chain in front of every request. A security filter chain bean declares which URL patterns need which role, health checks are open, admin routes need the admin role, everything else just needs to be authenticated. And passwords are never stored plain. Bcrypt password encoder salts and hashes each one, so two identical passwords produce two different hashes. URL level rules cover whole patterns, but sometimes you need to guard one specific method. A preauthorize evaluates a Spring expression before the method body runs has role for admins, or a check that the path variable matches the logged-in user's own ID. It runs on top of the filter chain, not instead of it. That's the data and security layer: sorted derived queries, explicit JPQL, pagination, and 2 layers of authorization. Next, what happens when that one service becomes 5, and they all have to talk to each other reliably? Splitting a monolith into services solves some problems and creates new ones, finding instances, surviving a downstream failure, and keeping data consistent without one giant transaction. Instead of every client calling 5 services directly, they all call one API gateway, which routes requests to the right backend and centralizes concerns like authentication and rate limiting in a single place. A route just maps a path prefix, like /orders, to a load-balanced service name. Clients never need to know how many services actually exist behind it. In a monolith, calling another module is just a method call. In microservices, calling another service means finding where a healthy instance of it is running right now, since instances scale up, restart, and redeploy constantly. A service registry keeps that live directory, so code asks for order service by name instead of hardcoding a host and port. When a downstream service is slow or down, hammering it with retries just wastes threads and spreads the failure upstream. A circuit breaker tracks the failure rate, and once 50% of the last 20 calls fail, it opens further calls, skip the network entirely and go straight to a fallback, until a wait period passes and it cautiously tries again. A single database transaction can't span multiple services that each own their own database. The saga pattern replaces that with a sequence of local transactions, each publishing an event that triggers the next step. If payment fails after the order was created, a compensating action cancels the order, instead trading strict consistency for eventual consistency. And each service owns its schema outright. If inventory needs order data, It calls the order services API or subscribes to its events. It never reaches into that table directly. That's what keeps 5 services independently deployable instead of one tangled shared database. Gateway, discovery, circuit breakers, sagas, and separate databases. That's how services survive contact with each other in production. Now let's look at what's changed inside a single Java process for handling concurrent work. Modern Java gives you real tools for concurrent work beyond raw threads, composable async pipelines, and, as of Java 21, virtual threads that make blocking code cheap again. A completable future represents a value that will exist eventually, and instead of blocking at every step, you chain transformations onto it. Then apply transforms, a plain result applying a discount to an order, say. Then compose is for when the next step itself returns another future, so you flatten the chain instead of ending up with a future nested inside a future. Then combine joins 2 independent futures once both finish fetching a price and a stock level in parallel, then merging them into one summary. And when you've got a whole batch of async calls instead of just 2, Olive waits for every one of them to complete before you safely pull each result out. Left alone, an exception inside the chain propagates all the way to the final get or join call as a wrapped exception. Exceptionally only fires on failure and supplies a fallback value. Handle fires either way, giving you one place to normalize a success and a failure into the same shape. A platform thread maps one-to-one to a real OS thread, which gets expensive fast. A few thousand is already pushing it. A virtual thread is JVM managed and practically free. You can spin up 10,000 of them without rewriting anything reactive, because ordinary blocking code like thread.sleep or a JDBC call just works, unmounting from its carrier thread whenever it blocks. Structured concurrency takes that further. A structured task scope treats a group of subtasks as one unit. Fork a task to fetch the user and another to fetch their items. If either one fails, the scope cancels the other automatically, so you never end up with orphaned background work still running after the operation that started it is gone. Composable futures for readable async pipelines, virtual threads for cheap blocking at massive scale, and structured concurrency to keep it all accountable. None of that matters, though, if you can't prove it actually works, which is where testing comes in. 3 levels of testing, each verifying something different: a fast mock, a real Spring context, and finally a real database running in a disposable container. Mockito creates fake versions of a class's dependencies so a unit test can isolate just the logic you're testing. When then return stubs what a mocked call gives back, verify confirms a method was actually called, and how many times. None of this touches a real database, which is why a whole suite of these runs in milliseconds. A unit test isolates one class. An integration test boots the real Spring context and drives a request through the actual controller stack. Real routing, real validation, real JSON serialization using MockMvc, which does all of that without opening an actual network socket. Mocking the repository is fine for service logic, but eventually you want proof your queries work against a real database engine, not an in-memory stand-in that behaves subtly differently. Testcontainers spins up an actual disposable Postgres instance in Docker just for that test run, and tears it down the moment the test class finishes. Milliseconds fast mocks, Spring-aware integration tests, and real containers when it counts 3 tools, 3 different jobs, and together they're what makes shipping the rest of this level safe. That's level 4 end-to-end production-grade Spring data and security, the architecture patterns that hold a microservices system together under failure, the concurrency tools that make modern Java genuinely scale, and the testing discipline that backs all of it up. Every code sample here came straight from the Java Mastery Path lessons, linked below in the order we covered them. Go read the full modules, run the exercises yourself, and you'll walk away with more than you could from watching alone.